5 o'clock. For the last talk, we have Yifei Huang, who is not from Cornell University. This is from Rice and University of Southern California. So please go ahead.
Thank you for the introduction. And today we're going to talk about another extension of the regular expression, the so-called semantic regular expressions. So we're in the CAT session, so I believe most of the people in the room are actually know regular expression better than me. Like, it's a very powerful tool for pattern matchings, but there are like these kind of questions that you cannot really just use regular expressions, right? For instance, like you can use regular expressions to find out all the URLs in the text file, but you cannot really tell if it's responsive or not, or maybe you can find the string literals, but you can't really tell if it's looks at the password. But there are really like other tools. For instance, like you can use the HTTP client or a LLM to decide to answer these kind of questions. So the idea of semantic regular expression is that if we can extend the regular expression to allow it to have the power of talking to an external oracle, it would be largely improve its expressiveness. So over here is that you can basically we give the ability of the regular expression to like talk to an external oracle. So once it's a simple formalism, it's actually very simple. So we're only introducing one more construction in this syntax based on the classic regular expressions, where you have this so-called refinement operator. And the semantic of it is really just an intersection of the whatever is accepted on the left-hand side, which is also a SEMRE, short for semantic regular expression. And the right-hand side is just the oracle queries, where like we're modeling this oracle as a arbitrary function, just take a query string and input string and return a Boolean value. So here, we treat oracle as a total black box. We're not assuming any kind of underlying distribution of the input and output. So it can be anything. It can be a SQL query, it can be LLM, whatever. All right, so one thing to notice is actually this formalism allows any depth of nested queries. So basically you can, so here's a SEMRE is basically asking whether there's a celebrity name whose name also has a city in the top of it, so which Paris Hilton would be an example. And to be clear, that this is not our new idea. There's this amazing work back in 2023 where they're using semantic regular expressions to perform data extraction. But in their paper, they're more focused on the synthesis part. Where here we're talking about more fundamental problems. That's once you synthesize this SEMREs, how you're going to really use them in the practice, right? You really want it to be able to perform the matching quickly. So that's why it brings us to the question of the membership testing for semantic regular expressions. Whether you're given a SEMRE R and the input string W, you want to like determine if W matches R. And of course, like in this algorithm 101 class, is this classic example of using dynamic programming to evaluate regular expression. We can do the same thing over here, or you have to do just like do the dynamic programming based on the AST and there's semantics. But it's very easy to write. I mean, you can write it in an afternoon, but the downside is that it's actually not very fast. It's actually cubic time and it doesn't stale at all. And we all know that for these classic regular expressions, we have this fancy NFA-based algorithm that runs very fast. It can run in linear time. That's actually the reason why regular expression is useful after all, because it's very fast. I mean, when you type grep, you grep out everything very quickly. So let's just do a very quick recap of the NFA algorithm. So we have to do just take the regular expression and do this very classic Thompson-style transformation to the NFAs. And right now, what you have to do is just like you want to determine if there's a path from start to end that encode the same input string W. So the question here is like how you're going to determine such paths if such paths exist. And for regular expression NFAs, you can do this iterative calculation of the frontier set. And basically, you start from the initial state, and after you're parsing the entire input, you want to see if the final state is contained in the frontier set. The secret why this algorithm is very fast is that the state space is just the frontier set is just a subset of the NFAs. So which means that at every step, the burst time complexity and space complexity is bounded by the size of the NFA. So this means that to process the entire input, it only takes a linear time. And the other way of looking at it is actually where, for the frontier, we only care if a state is reachable or not at any certain step of iteration. So basically, let's say you have like two tokens like performing epsilon transitions reaching the same state. You can eliminate any one of them because we only keep any one of them. So you can basically just discard any one of them. But we'll see that in SEMRE, this is no longer the case. So I mean, since we have this very good NFA algorithm, why don't we just extend it with SEMRE and see? Let's take a look at how it really works. So just like what we did for the to the definition of the SMREs, we just introduce a new construction to the NFA that becomes the so-called SNFA. Right now, we have two new kind of nodes where like there's an open of the query queue and a close of query queue. So which basically acts like a punctuation mark, just marks the boundary of the query. So when you really enter a state, open state, and you're now starting to accumulate a query, and when you exit at the close node, you're going to discharge that query. So right now, we're looking for passes not only that is W labeled, that is input labeled, the pass has also to be feasible. That is to say that all the encoded query along this path has to be accepted by the oracle. So how do we efficiently determine if such pass exists? So let's take a look at this example. Here's a very simple SMRE. Admittedly, this is not the good SMRE you want to write, but it's simple enough for the purpose of demonstration. So this is a possible SNFA that is corresponds to it, and we have an input string over here that says mid push at 4. We know that this string belongs to will match by this SMRE because we know push is a partition. So let's see what will happen if we try to like just feed this string into the SNFA, just what we did to NFA. So see over here is that at here this state at 0, you can choose to either enter the query boundary to S1 or just stay in itself. So let's say let's say two different passes when we feed this string to the SNFA. There's like this yellow and blue chassis, and the blue chassis is determined to enter the query one character earlier. So this ends up making the two chassis is actually encoding two different queries, and one is that whether T push belongs to is a president or whether push is a president. So the problem here is that there are two actually, or you'll get different results from the oracle. It actually affects your result for your matching. So it means that when you are like doing this iterative frontier calculation, you will have to keep all these chassis, because the problem here is that right now the token will carry some context information, and if you really do it naively, you will blow up the state space, and you're not going to do that in a reasonable amount of time. So how are we going to solve them? So our solution is a two-pass algorithm. So basically, first we convert the input string W and the SNFA into a data structure, which is so-called a query graph. That's kind of unroll the input and just we distilled out all the query structure, and then we just verify the satisfiability over this new data structure that we call the query graph. All right, so what is a query graph? So pretty simple. It's a well-periodicized monotonically increasing DAG. Well, this is not simple at all, admittedly, but I'm going to show you that it's actually very easy to understand. And it's just, you can think about it as an SNFA, but with the label removed. They're only epsilon transition right now. So here's an example of it. You see right now we don't put any kind of characters on the edges, but right now we put numbers on the query boundaries. Right now you have these numbers, which is actually the index of the input string, because the query graph is binded to a specific input string. So let's say we have this red passes over here. So when it's in the SNFA, we said open and close. You have to look at the labels in the edges between them. But right now, you only have to look at the substring 2 and 3 over here, because you already have them indexed in the nodes. Here, this green pass is encoding the query of the empty string, because you're looking at the substring 3 as 3. So you can see about each of these passes, it's a conjunction of the queries. And because it's a DAG, so you only have a finite number of passes, so the number is very large. But you can actually treat it as a very huge DNF formula. And this query graph is a very compact way of representing it. So first, it's that we'll have to like unroll the SNFA to like get this query graph. So the idea is really that we are kind of unrolling the inputs. The input paths in the SNFA. The question over here is that each input path will corresponding to infinitely many passes in the SNFA, because we know there's like loops that is introduced by the clean start operator. But the key observation over here is that all this complication happens when you're performing the epsilon closure. And let's see, I mean, in the epsilon closure, you might like enter a path, open, close it, close it, close it, open, open, or something. But the idea is that even though there's like infinitely many of them, their behavior or the queries they ask can be actually encoded into a finite set of equivalent classes. So basically, there's like open and closes, they kind of cancel out, because there's just corresponding to a query to an empty string, and you can just pre-discharge it earlier. And eventually, all these paths can be summarized by a series of close and series of open. And this number is actually bounded by the sets of depths. That is just the way how you return the SNFA is predetermined. It's a constant. So we kind of if we can summarize all these possible transitions, we build this kind of structure, which we'll see earlier is just the key component of the query graph that kind of summarize all the possible epsilon transitions to the query context change, and this is what we so-called the inter-character gadget. So over here is this is a step that's just, we build a query graph that looks like the way you evaluate as an NFA. So we have this gadget that is capturing all the epsilon transitions and all the context change over them, and we kind of glue all this gadget with the character transitions. And so this is the state where you kind of unroll the input string W and form this query graph. It looks very large over here, but it's actually linear to the size of the input. So that's why we can, it allows us to perform the computation in the reasonable amount of time. So that's a phase 1. And phase 2 is how we evaluate the query graph on it. So just similar to the SNFA, we can also define the satisfiability of the query graph. So for now, we can also define the definition of the feasible path, where you have a path in the query graph, and all these encoded query are accepted by the oracle. So now the problem is that how we're going to determine if the feasible path exists in this query graph. So notice right now this query graph, unlike SNFA, it's a DAG, so we eliminated all the loops. So the good thing is that right now we can perform dynamic programming on it just by the topological sorting. And so the idea is actually very simple. We introduce some definition, but all we care is that whether we have a feasible path from all the way from start to end. And we kind of extend this idea to every intermediate node. That is to say, we want to know, we say a node is alive if there is a kind of a path that goes from the start to it with all the queries that is accepted. Well, here we use the word tentatively feasible is because at the intermediate node, you might have a path that reach to it, but there are some queries that are not closed yet. But the problem is that as long as all the discharge query are accepted, we treat this node as alive. So all we have to do is just like you use DP to calculate whether the end node is alive or not. So the rule of the dynamic programming is really not that hard, especially for the start and blank and open nodes. But the tricky thing is that when you encounter a closed node, you have to, basically, you're starting to discharge queries, and you have to know what are the queries you have to discharge. So you have to have a way to efficiently look up all these paired opens. And here is that along with the dynamic programming, we maintain this data structure, the so-called back reference. It's just a way of like recording what is the closest open node along each path. So the idea is that once you close something, you're going to immediately update this back reference set. And unfortunately, the calculation of it will involve a operation that just close to a Boolean matrix vector product, which eventually becomes the bottleneck of our algorithm. So let's see how this algorithm really performs. So let's assume the oracle response in constant time. Everything before the query graph evaluation is actually in linear time. We build a query graph in linear time. But the thing is that this back reference calculations brings the algorithm all the way up to cubic time. So this is a summarization of the complexity. We can actually see that for the last two columns, for the unambiguous MREs or like the no-nested cases where you don't have like two queries nesting each other, the performance is actually really well. It kind of matches the lower bound. For instance, the lower bound is quadratic because let's say you see the president SMRs before. It's like in the worst case, you have to query all the possible substrings. That's actually in the magnitude of quadratic. But since when presenting this algorithm to an advisor is that, well, I mean, we already have a good result for some common cases. Why we can't just do it for the general cases, right? So we're going to defend this result in two ways. First is that, asymptotic complexity is not necessarily always the best measurement. So let's just do some experimental evaluation. We collect this two huge set of the input data, some spam email corpuses, and some Java code from GitHub. And we build 9 different SMREs with all the variants of the Oracle backend. We have 5 different of them. And we evaluate their throughput with the size of as the size of the input increases. And this is our main result, basically demonstrate how this algorithm scales with respect to the input. So let's zoom in and take a look at one of them. So the x-axis is really the size of the input, and the y-axis is the logarithmic scale of the reciprocal throughput. That's just basically the time taken to process each line. So as you can see over here, our algorithm is constantly better than the baseline, And actually, our algorithm, you can see that the slope of our algorithm is actually it's even smaller. It means that our algorithm is actually asymptotically better. This actually matches our previous analysis because all these benchmarks are actually a common non-nested cases, which is quadratic in the complexity, but the baseline is actually cubic. Also, we might be interested in the number of oracle calls you have discharged because we know LLM are very expensive to learn, so there's some oracles that are backed by LLM. So, and we discovered that overall we make like 51% fewer of the oracle calls. All right, here's the experiment result, but we're in PLDI, we want some series result, right? So, where my advisor at this point is not 100% satisfied. So let's define my result even further. We prove that doing anything better in general cases, that is better than cubic time will be very challenging. So how do we usually do that? Well, we find some questions that is related to it. Remember that the bottleneck is really introduced by this Boolean vector, matrix vector multiplication. And there's one related problem to it is just the very famous problem in the graph series, that's the so-called triangle finding problem. That all you have to do is just give an undirected graph and you decide if there's a side-3 cycle, that's basically a triangle. Of course, you can write these 3 nested loops, this very trivial implementation, but you will take cubic time. And if you're doing it more carefully, you can do this. You can calculate the cube of the adjacency matrix and just look at the diagonal element. And if there's a 1 over there, it means that you can have a loop of size 3 that goes back to itself. And if you do this with fast matrix multiplication, you will be able to do this, to do triangle finding in subcubic time. But it turns out this is the best thing you can do because there's actually no-no and combinatorial algorithm. By combinatorial, I mean this algorithm that doesn't involve fast matrix multiplication like Strassen, because those are not very practical. And the best thing you can do over here, the practical algorithm is actually running in cubic time. So what we have to do is just like link this problem to our problem. And the idea is that if we write out the graph like this, and all these 3 vertex tuple can be actually witnessed by ABC over here. And if we linearize the graph into a string like this, you can actually find all the 3 vertex tuple in this string as a substring over them. So all you have to do is just write a SMRE that looks for the substring where it is corresponding to a triangle. And it's very easy to do. All you have to do is just build an oracle that's just test if the 2 vertices are connected or not, and build this SMREs that basically you're looking for if the AB is connected, BC is connected, and AC is connected. Notice that this SMRE is a general case. It's a nested SMRE. So right now all you have to do is feed this input to this R triangle, and you will determine the membership for it. And if you can do this thing, anything subcubic time, practically, you're actually solving the triangle finding problem. So that's why it's very hard to beat the general bound. Okay. So the conclusion, to summarize, we formalize this idea of semantic regular expression. We present these 2 passes algorithm that based on the NFA, and it's practically working very well, and we prove a harness result for the general cases. And you can find the artifact in the QR code, and thank you for your listening, and happy to take any question.
Thank the speaker. All right, does anyone have any questions? Really? Well, I have a question. I have to have a question. I'm a sessions chair. Oracle, huh? Database, I understand, but LLM, remember you had examples. Mm-hmm. That's non-deterministic, is it?
Yes. So, you're right. I mean, it's not deterministic. So in our evaluations, we kind of frozen the result produced by the LLM. So basically, once you produce it, the result is cached, and it's frozen over there. But yeah, indeed, this is a very good observation, and because the result by the LLM is just a distribution of the output token. And one natural future question is like, what if you have the oracle returning a distribution of the output, and then the membership testing will be a probabilistic problem? And this is actually one interesting question we're looking at right now.
Cool. Oh, thank you, Julian.
Is any non-trivial lower bound known on triangle finding if you're allowed to do anything?
What do you mean by if you're allowed to do anything?
Like you are allowed to use Strassen, for example, or any algorithm you can think of. Is there a non-trivial lower bound in this problem?
So I think it's like if you restrict the type of graph For instance, if the graph is sparse or something, you might have a better lower bound. For general graph, you don't have any restriction of the graph, I think you can never do anything subcubic without using fast matrix multiplication. So right now, the only lower bound is just the fast matrix multiplication in general cases. But those are anything subcubic will be very impractical, right? Those Strassen-like approaches.
So is there anyone who has proved that you cannot do it in linear time, triangle finding?
The graph is already cubic. The resistance matrix is already cubic. It's quadratic, so of course you cannot do it in linear time.
Another question I had is experimentally you show the slopes.
Mm-hmm.
Do those actually correspond to your worst case bounds, or is that
it actually corresponds to our worst case bound because here the benchmark are no-nested query. Those are quadratic, and that matches our observation.
Thanks. Very nice talk.
Thank you.
Hi, I had a quick question about space complexity. Do you have any theoretical results, or maybe even experimental results, about how much space and memory this takes up?
I don't think, we don't really have evaluation on it, but I think the space complexity is just more or less the same as time complexity. You don't really have to, store a lot of information I mean, you have the query graph, that's the largest thing, but actually you can represent it in a very compact way because the gadget is kind of duplicated. So I would say it's actually, the space complexity will actually be linear to the size of the input, yes. Or maybe some intermediate state DP might go to quadratic, but it will never be cubic. Yeah, I think.
Thank you.
Thank you.
So this may be a dumb question, but I think you mentioned during your talk that you assume the oracle call is O1. I wonder if, because like you also mentioned like oracle can be larger than models, I wonder if you can do some analysis that assumes that the oracle call is actually very, very expensive. You want to minimize that.
Yeah, that's a very good question, and that's actually our subsequent work. Of course, if you have backend like, usually, I mean, initial work have their backend as LLM, which are super expensive to call. And actually, if you really run things with LLM backend, you will see the bottleneck is actually LLM itself. So it's very natural in that case to like replace the O1 with the actual complexity. But in that case, we're not talking about a black box oracle anymore. You have it's actually a gray box or a white box because right now you have access to the distribution of the tokens in LLM or some like the query structure in the SQL query. Over then, you can do like case-by-case optimization to the algorithm. But yes, that's a very good future direction. But this paper, we're only focusing on black box oracle. So we cannot make any assumption on it.
Thank you.
Well, thank you. Let's thank the speakers. Thank you very much. And,